When 3I Atlas completed its solar flyby in late October, most scientists believed the story would be over. The trajectory was hyperbolic. The radiation levels it encountered near perihelion were lethal to any known cometary structure. By all current models, it should have fragmented, its volatiles stripped, its core broken apart into a cascading field of dust and silence. Instead, it did something no one expected. It didn't die, it adapted. In the hours following perihelion, space-based observatories monitoring the object began reporting stability. Not just structural integrity, but unusual calm. There were no rapid jet emissions, no tumbling debris, no evidence of violent surface loss or outgassing spikes that typically mark a comet's closest solar approach. Instead, 3I Atlas emerged from its solar encounter more organized than before. Its reflectivity increased, its shape remained coherent, and most importantly, its motion began to change, not erratically but with a slow, deliberate precision. This behavior did not fit the profile of a natural comet. In fact, it broke every expectation. Normally, the sun's heat initiates sublimation, a process where surface ice transitions directly into gas, releasing jets that push comets in unpredictable ways. These jets often induce chaotic spins, uneven torque, and fragmentation over time. But with 3I Atlas, there was none of that. Instead of reacting with chaotic volatility, the object showed signs of regulation. It was as though it had prepared for the encounter, as if it had absorbed energy, not merely survived it. The first major anomaly came from the Parker Solar Probe, which was in a favourable position to measure solar-wind interactions near the object's path. It recorded a small, localised compression in the plasma stream, a ripple that passed within minutes of 3I Atlas's closest approach. While subtle, the signal was real. More concerning, however, was what followed. Over a span of several hours, instruments aboard multiple satellites, including ESA's solar orbiter, recorded a shifting electromagnetic footprint in the wake of the object. A faint but consistent field disturbance, not unlike what you'd expect if something had briefly carried a magnetic signature through the solar zone. Then came the optical irregularities. Astronomers on Earth began detecting a glow, not from the tail, but from the core itself. A sharp, white fuselage-like centre, wrapped in an artificial-looking blue hue. When amateur astronomers posted the first backyard photos online, professionals dismissed them at first. But then Hubble confirmed it. The object's nucleus was too bright, too smooth, too structured to be explained by sublimated ice alone. And the colour, that soft, unnatural blue, was not consistent with any known chemical emission from standard comet materials. It looked more like reflected plasma or contained energy. Scientists at the European Southern Observatory ran a full photometric curve analysis. The light profile didn't match a coma. It didn't match an expanding dust cloud. It was directional, pulsed, consistent with a surface designed to reflect, not emit. The implications were serious, but difficult to accept publicly. And yet the most startling detail wasn't the light. It was the motion. As 3I Atlas moved away from the sun, its speed began to drop, ever so slightly. For a hyperbolic object, that's not supposed to happen. It should coast, untouched except by solar wind and weak gravity gradients. But 3I Atlas slowed down. Not in a way that suggested friction or debris interference, in a way that suggested manoeuvring, as if it had absorbed solar energy and was now using it, not to escape, but to begin the next phase of its trajectory. That phase wouldn't take long to reveal itself. Because only days after this solar encounter, something began to change in the sky, not in 3I Atlas itself, but in the objects around it. Dormant comets, once silent, inactive, suddenly lit up, and every one of them was in its path. The sun didn't destroy 3I Atlas, it awakened it. And what it did next would shake the foundation of what we thought we knew about our solar system. On the morning of December the 12th, just days after 3I Atlas completed its solar departure, something unprecedented happened in the outer solar system. At first it looked like noise, a single dormant comet flaring unexpectedly. Then, within hours, a second one followed. By the end of the day, 5 separate objects, all previously catalogued as inactive, had simultaneously become active. They weren't near the sun. They weren't near any planetary gravitational slingshot. And none of them were forecasted to erupt. Yet they did. All at once. Astronomers watching the real-time data stream from the Minor Planet Center saw the spike. 5 entries, each separated by less than 6 hours, flagged with rapid brightness increases and unexpected outgassing trails. The comets, each with previously dormant profiles, were now radiating volatile jets and forming visible comae. That alone would have been strange. But what made it chilling was their proximity, not just to one another, but to a moving line that traced back to a single object, 3I Atlas. This wasn't a random outburst, it was a pattern. The comets were located in a loose arc between Mars and Jupiter, inside the main belt's outer edge. Spatially, they appeared scattered, but when you overlay their activation times with the recent outbound path of 3I Atlas, a shape emerges, a crescent. Every activated body sat within a spherical distance envelope no larger than a few million kilometers across. In cosmic terms, that's like having 5 campfires suddenly ignite in perfect rhythm on a frozen field, right after someone walks through it. But even that analogy misses something deeper. These weren't old-world comets being pulled into activity by solar warming. Their activation sequence followed a rhythm. The first object flared at 02:16 UTC, the next precisely 44 minutes later, then again and again, until the 5th object pulsed into brightness almost exactly 3 hours after the first. The pattern was unnerving in its regularity. Scientists began comparing it to pulse codes, telemetry bursts, or signal sequences. It didn't look natural, not like random dust impacts or delayed solar heating. The spacing, the timing, the alignment, all pointed to an outside influence. The only candidate in range, 3I Atlas. The object had passed through that same region only 27 hours earlier. During that passage, no visible interaction had been detected. No jets, no proximity alerts. But what if the interaction had been dormant? What if 3I Atlas had simply seeded them? The idea, once science fiction, now had data behind it. Each of the activated comets began to show structured jetting. Not random venting from multiple points, but focused singular emissions. And more disturbingly, each of those jets pointed back toward the solar vector, not away from it. It was as if they were being powered up in sequence, and possibly being aimed. Radar scans were immediately redirected toward the region. Though resolution was limited due to distance and angle, what returned raised eyebrows. The reflectivity profile of each newly active object had changed. They were now reflecting more light, in tighter frequency bands than before. A sign, possibly of surface modification, of coatings or panels. As the data compiled across observatories in Chile, Hawaii and Tenerife, a working theory emerged. The comets hadn't activated due to solar radiation. They had been triggered, either remotely or by proximity to a system capable of depositing energy or materials capable of delayed ignition. Whether that ignition was chemical, electromagnetic, or something else entirely remained unclear. But one fact was undeniable. 5 comets that had been cold and silent for decades had erupted with synchronized directional behavior. And the only variable introduced into that region in the previous day was 3I Atlas. This was no longer a comet behaving strangely. It was becoming a system. Following the sudden activation of the first comet cluster, astronomers around the world turned their attention not just to the objects themselves, but to their surroundings. What they found defied basic cometary physics, because in the wake of those 5 reawakened bodies, space wasn't silent, it was humming. Infrared telescopes, including those at Mauna Kea and the European Southern Observatory, began sweeping the activation region across multiple wavelengths. Their goal was simple: measure the thermal emission profiles of the dust and gas now streaming from each body. Typically, when comets awaken, they eject volatiles that warm and scatter under solar radiation. The result is a predictable heat curve, warmest near the nucleus, with a gentle fall-off across the coma and tail. But that's not what the instruments recorded. Instead, they detected concentric waves of temperature, shells of warmth rippling outward from each comet, not evenly, not chaotically, but layered, like tree rings in motion. Even stranger, the temperature fluctuations didn't radiate outward at light speed, or even heat speed. They moved in timed pulses, short bursts, like echoes. This wasn't thermal diffusion, it was release. Scientists dubbed the phenomenon dust echoes. The term was imprecise but descriptive. It appeared as though each comet had not just ignited, but had emitted a series of controlled pulses into the surrounding space. These were not gas bursts from internal pressure. They were layered emissions with pauses between them, and more crucially, all 5 objects pulsed in rhythm, almost as if they were part of a shared timing network. The echoes, when mapped, showed something else: directional alignment. In every case, the denser particles were being ejected not radially, but in narrow corridors, forming what looked like artificial lanes of dust. When visualized across time, these lanes fanned out like searchlights, sweeping in unison across a shared quadrant of space. Their endpoint, the region through which 3I Atlas had passed just a day before. This behavior baffled planetary scientists. In natural cometary outgassing, the dust jets follow thermal gradients. They are messy, diffuse, and strongly influenced by the rotation of the nucleus. But in this case, there was no spin-induced wobble, no random diffusion. The particles were acting like they were being steered. Radar reflection data from Arecibo's backup tracking array was analysed next. It revealed a consistent signature in the surrounding dust. Particles clustered at regular intervals spaced apart with mechanical precision. This was not the chaotic debris field of a sublimating comet. It was order, repetition, a grid. NASA's dust particle simulation team was tasked with modelling the pattern. They attempted every known explanation: differential heating, micro-impacts, plasma charge separation. None of them could replicate the sequence. Only one model came close, one involving phased particle emission from a rotating aperture. In other words, a nozzle, or something very much like one. As the data mounted, a new theory began to take shape among a small group of physicists. What if the dust wasn't just a byproduct of outgassing? What if it was being used to communicate? Dust carries charge, dust carries mass. In the vacuum of space, it can behave like a canvas, or like a carrier. And if multiple bodies are emitting synchronized patterns, those emissions might not just be visual, they could be encoded. The possibility raised more questions than answers. Could this be a kind of intercomet messaging, a feedback system, a signal relay? Or something stranger still, a mapping of the space itself, a way to trace paths like breadcrumbs across orbital lines? One thing was clear: these echoes weren't random, they weren't passive, they were deliberate, and they all pointed in the same direction, the one 3I Atlas had already travelled. In the dust, the silence was gone. It had been replaced by rhythm, and rhythm implies memory, intention, system. Something had spoken, and space was still reverberating with its message. By the evening of December 12th, the global astronomy community had moved from observation to correlation. What began as 5 isolated comet activations now revealed something far more coordinated. Across every data stream, light curves, magnetic readings, thermal scans, one truth was becoming undeniable: the events were not independent, they were synchronized. The timing between the 5 cometary activations was the first major clue. Each body flared to life at precisely 44-minute intervals. Not approximately, not roughly, exactly. The delay between each ignition was so consistent that software designed to analyze pulses began flagging the sequence as artificial. The chances of such timing happening by random chemical reawakening across different bodies of differing mass and distance bordered on statistical impossibility. What deepened the mystery was that these were not symmetrical events. Each activation was offset not only in time but in vector. When plotted in 3-dimensional space, the positions of the comets formed a spiral, a helix that unwound perfectly along the previous trajectory of 3I Atlas. That spiral wasn't decorative. It was aligned to a very specific orientation, perpendicular to the solar wind flow, meaning whatever triggered these comets, it had considered solar interference and avoided it. This is not how nature behaves. Thermodynamic chaos does not generate spirals with mathematical symmetry. Chemical volatility does not respect timing windows. Gravity alone does not guide dust jets to align like clocks. And yet, here it was, 5 separate cometary bodies acting like they were wired to the same internal metronome. Spectral scans from the James Webb Space Telescope offered more. Each activation was accompanied by a unique flash, a sharp spike in brightness lasting exactly 1.3 seconds. The light was not consistent with standard volatile outgassing. It had a hard wavelength cutoff, emitting narrowly within the ultraviolet range, then vanishing. These flashes appeared just before each comet erupted, not after, meaning something primed them or triggered them. But what linked them all? The answer came from an unlikely source: radio observatories in Australia monitoring low-frequency sky noise. Buried deep in the background of the activation zone, a set of pulses was detected. Short bursts occurring 44 minutes apart, lasting less than a second each. Not strong enough to suggest a transmission, but clean enough to exclude natural background. The signal strength wasn't enough to triangulate a source, but the directionality was clear. The origin traced back to 3I Atlas. Suddenly, the spiral made more sense. If 3I Atlas had passed through this region, emitting low-frequency pulses or depositing material that responded to a delayed command, then the geometry of the cluster wasn't just a byproduct. It was a map, a layout, a formation. The idea was simple but staggering. 3I Atlas had seeded these objects, and now it was waking them up one by one, on a schedule. Researchers at the Max Planck Institute ran orbital reconstruction models, using activation times and inferred trajectories. When projected backward, all 5 objects shared one key moment. They passed within a narrow window of 3I Atlas's outbound path roughly 27 hours before they activated. They weren't random comets. They were dormant, perhaps inert, until they came into contact with something, material, energy, or command. And the most chilling part: the model predicted a 6th activation. If the pattern held, the next object in the spiral, further out, more distant, would light up just before dawn UTC on December 13th. Same time delay, same trajectory, another flare, another echo. The world waited, and right on time, the 6th comet ignited. 6 objects, same pulse rhythm, same directional alignment, same strange jets. This wasn't behavior. This was orchestration, and something was conducting it from the dark. In the early hours of December 13th, as the 6th comet lit up exactly on schedule, a parallel anomaly emerged. This time not in the cluster, but in 3I Atlas itself. Tracking stations across Earth's hemispheres, including the Jet Propulsion Laboratory in California and the Subaru Telescope in Hawaii, began to register a change in the object's motion. But it wasn't dramatic. It wasn't the kind of violent course correction you might expect from an external impact or sudden burst. It was quieter than that. Subtle, purposeful, a measured change in velocity, downward. 3I Atlas was slowing down. That by itself is not unprecedented. Outgassing can alter an object's trajectory. Solar radiation pressure can nudge interstellar bodies slightly off course. But this wasn't a random deviation. This was deceleration. And it wasn't radial, meaning it didn't move away from the sun or curve under gravity. It was directional, aligned precisely with the corridor of recently activated cometary bodies. Slowing down in space is not trivial. In a vacuum, an object continues on its path unless acted upon. And the only forces known to influence an interstellar object mid-transit, besides gravity, are solar pressure and internal sublimation. Yet 3I Atlas had already passed its solar peak. The heat was behind it. Outgassing, if anything, should be fading. But instead of speeding up, as would be expected post-perihelion, it was tapping the brakes. This behaviour immediately caught the attention of the European Space Agency's Deep Space Dynamics Division. Using Doppler-based trajectory refinements, they confirmed that the object's heliocentric velocity had dropped by nearly 2 meters per second over a 3-hour window. That may sound negligible, but at interstellar speeds, even a slight deceleration requires energy and coordination. The big question became, why? Why would 3I Atlas slow down now, just as the cluster was activating? Why reduce velocity in open space, unless to match or align with something nearby? The answer came from a deeper orbital model. When superimposing the newly calculated deceleration vector onto the expanding spiral of active comets, a pattern emerged. The arc of the slowdown wasn't arbitrary. It paralleled the spatial curve of the activated cluster. It was as if 3I Atlas was adjusting not just course, but tempo, like a conductor stepping into sync with the musicians it had just awakened. Even more unusual was how the slowdown occurred. Most natural cometary velocity changes are jagged, resulting from chaotic venting or surface irregularities, but the velocity curve from 3I Atlas was smooth, linear. It followed a Gaussian decay curve, something not seen in natural outgassing but often used in engineered throttle control. At this point, whispers began to circulate in closed scientific channels. Was 3I Atlas navigating? If so, what was it aligning to? A new round of spectral analysis was initiated. Observatories began scanning for reflected radio bursts, UV signature anomalies, and infrared variations. Though results were preliminary, one detail stood out. During the deceleration phase, the reflectivity from one hemisphere of 3I Atlas increased slightly, as if a surface had rotated or deployed. Theories flooded in: a sail, a brake, a shield. No consensus emerged. But the timing was too close to ignore. Deceleration began just hours before the sixth activation. Then, once the sixth object lit up, the velocity stabilized. The slowdown ended. It looked like rendezvous. Not in the traditional sense, with docking or physical contact, but in orbital behavior. The kind of precision we see in autonomous satellite formations, micro-adjustments to maintain distance, spacing, and sequence. And that changed everything. Because if 3I Atlas was slowing down intentionally to remain near its own activated cluster, then this wasn't a passive object. It wasn't just seeding and moving on, it was staying. And whatever it had started out there, it now intended to watch, or guide. As 3I Atlas adjusted its velocity and hovered near the reawakened cometary cluster, new instruments turned their focus to a phenomenon previously dismissed as cometary noise: the halos. But what astronomers began to observe from multiple vantage points around the world and in orbit would change that assumption entirely. Each of the 6 reactivated comets, along with 3I Atlas itself, developed a visible halo, a faint, translucent sphere of illuminated material extending well beyond their cores. But these halos were not the chaotic clouds of ice and dust typically associated with cometary activity. These were structured. They had edges. They pulsed with symmetrical intensity, and most disturbingly, they held shape. Standard comet halos, also known as comae, form from sublimated gases and microscopic dust particles expanding in all directions, driven by solar heat. They're uneven, ever-shifting, and rapidly distorted by solar wind and radiation pressure. But these halos behaved differently. Telescopes equipped with high-resolution polarimetric filters detected repeating bands of density within each halo. The layers were evenly spaced, concentric rings that looked more like atmospheric pressure waves than gas clouds. And they weren't fading with distance. Instead, they extended in geometric fashion, like nested domes. Researchers at the Infrared Telescope Facility, IRTF, in Hawaii, noted that the inner rings of each halo remained centered around a fixed point, despite nucleus rotation and local thermal variation. This suggested a form of confinement, as if the material wasn't being freely expelled, but rather was held within a field, a bubble, a boundary. ESA's solar orbiter, though not primarily designed for cometary study, captured a sweeping wide-angle image of the cluster region from a unique rearward angle. When the data was enhanced, the halos revealed something astonishing. They were all shaped identically, not spherical, but hexagonal. Hexagonal halo structures are virtually non-existent in natural space environments. On Earth, we only see them under very specific atmospheric conditions, such as ice crystal reflection inside high-altitude clouds. But in space, around objects with no atmosphere and no internal convection, it made no sense, unless the structure was being generated by something else. Further analysis of light scattering patterns showed that the dust particles within these halos were not behaving like passive matter. Their reflectivity was polarized, rotating in unison as the object moved. That kind of coherent polarization across such a wide area implied active alignment. Perhaps magnetic, perhaps electrostatic, but certainly not natural. At the Max Planck Institute for Solar System Research, physicists ran simulations to reproduce the observed geometry using known natural models: sublimation vents, asymmetric heating, nucleus rotation, even high-speed particle jets. None of the models could replicate the ringed halo formation. The only scenario that produced a matching pattern involved field containment, specifically a magnetic or electrostatic envelope around the object, guiding the dust into standing wave geometries. In other words, the halos looked like containment fields. If true, that would mean each reactivated comet, and possibly 3I Atlas itself, was using some kind of mechanism to shape and maintain its expelled material, not ejecting dust freely but trapping it, displaying it, perhaps even using it. A growing number of researchers proposed a functional interpretation. These halos weren't just visual anomalies, they were operating as shields, or more provocatively, as signaling structures. Because when observed at timed intervals, each halo exhibited brief pulses, short flashes, moving across the halo ring like ripples on a pond. The pattern resembled phased light emissions, like those used in LiDAR, scanning, or even optical encoding. The halos weren't just there, they were active, and all of them shared one orientation, not to the Sun, not to the galactic plane, but to Earth. Something had turned them toward us, and now they were broadcasting. As the dust halos expanded and stabilized around the reactivated comets, another layer of data quietly surfaced. This time, not from telescopes or visual sensors, but from magnetometers. On board both Earth-orbiting satellites and deep space observatories, a low-frequency anomaly began to emerge in the data. A localized magnetic shift, centered not on 3I Atlas itself, but on the region between the reawakened comets. At first, this shift was considered noise, possibly a reaction to minor solar wind fluctuations or the lingering effects of a recent coronal mass ejection. But as the readings were triangulated across multiple instruments, NASA's Themis mission, ESA's Solar Orbiter, and the China National Space Administration's Tianwen-2, it became clear. This disturbance was not solar in origin, it was local, it was precise, and it was moving. The region of magnetic turbulence was narrow, no more than a few thousand kilometers wide, and it passed cleanly through the center of the comet cluster. Unlike typical magnetic field changes, which show gradual gradients or chaotic turbulence, this anomaly was uniform, sharp. It appeared, intensified briefly, then faded within 4 hours, leaving behind a lingering resonance in the solar plasma. What stunned physicists wasn't just the intensity of the shift, it was its structure. When converted into vector fields and plotted in 3 dimensions, the disturbance revealed a perfect toroidal shape, a donut-like ring of magnetic flux with a stabilized core and evenly spaced field lines. Natural magnetic disruptions caused by solar wind or planetary interactions never take this form. They're messy, fluid, distorted. But this was symmetrical, balanced, engineered. The toroid was centered between the second and third activated comets, which had ignited 44 minutes apart. Their dust halos had already revealed structural containment patterns. Now, it seemed, the space between them had become more than just empty vacuum. It had become charged. Earth-based sensors picked up the ripple hours later. Deep geomagnetic detectors, including those at the South Pole Geophysical Observatory, recorded a brief micro-disturbance in Earth's upper magnetosphere. Nothing dangerous, just unfamiliar. It pulsed once, just before the toroidal structure faded. Theories formed quickly. The most cautious explanation suggested a synchronized outburst of ionized gas from multiple comets, interacting in such a way that the plasma fields overlapped and briefly generated an organized electromagnetic loop. But this required an implausible level of timing, pressure, and alignment, and it didn't account for the precision. Others proposed a far stranger model. What if the field was not a byproduct of comet activity, but a product of something linking them? An interface, a relay, a short-lived communications field that had to be generated while all 6 comets were still aligned in activation phase. A system designed to exchange data magnetically. One researcher from the Canadian Space Weather Centre compared the pattern to low-orbit tether experiments, where electric currents are induced along long conductive lines between spacecraft. The similarity wasn't perfect, but the field shape matched, and the energy required to generate the observed flux was minimal, if you had the right materials, and that brought the conversation back to surface composition. Spectral scans of the reactivated comets continued to show enhanced reflectivity, possibly metallic compounds, nickel, carbon alloys, rare volatiles. These weren't typical for frozen interstellar bodies, but if present, they could form a conductive ring, and if charged even briefly by electromagnetic induction, they could behave as antennae, or processors. If correct, this meant 3i Atlas hadn't just seeded the cluster with energy or motion, it had enabled interaction. It had turned inert rocks into a distributed magnetic network. The localized magnetic shift wasn't an accident, it was a handshake, and the system had just gone live. While the magnetic field anomalies captured headlines in scientific circles, another quieter discovery began surfacing, one that was visual, persistent, and impossible to explain with traditional cometry models. The surfaces of the newly activated comets were changing, and they weren't changing randomly, they were gaining structure. The first signs came from the James Webb Space Telescope, which had been tasked with capturing thermal and reflective data from the objects as they drifted deeper into the outer solar system. At first, researchers were focused on temperature profiles, looking for hotspots or energy leaks. Instead, what caught their attention was the light signature, the way sunlight was reflecting off the surfaces. It wasn't scattered like dust-covered ice, it was clean, sharp, and it showed repeating patterns. Each activated comet displayed distinct reflectivity bands, linear, angular, and consistent across rotations. When mapped across a full 360-degree spin, these bands formed grid-like arrangements, interlocking rectangles, symmetrical polygons, and in 2 cases, perfect, equilateral triangles etched into the dust-covered surface. The grid lines weren't deep enough to be craters. They weren't caused by erosion or venting. They appeared to be part of the reflective structure itself, etched just beneath the outer layer. Amateur astrophotographers using stacked imagery techniques were the first to suggest what professionals began to confirm. These surface markings weren't superficial, they were functional, they looked like access panels. But that was just the beginning. Ground-based radar dishes, including the Arecibo Successor Array and NASA's Goldstone Deep Space Network, pinged each of the activated comets with high-frequency radar sweeps. The reflections that came back were not what anyone expected. Instead of the diffuse granular radar return typical of icy or rocky bodies, the echoes from the surfaces were flat, specular, like bouncing a signal off a smooth metal hull. One echo from the third activated object, Comet 3i CL3, stood out. It showed not just uniformity but a phase shift, a brief delay in signal return across one section of the surface. That kind of shift requires one thing: density variation beneath the surface. In other words, a hollow zone. Engineers familiar with spacecraft design recognized the signature immediately. It matched radar profiles taken from orbiters scanning space stations, satellites, and even some planetary landers. A hardened shell with an internal cavity and a structured layout beneath. Multiple observatories repeated the test, and though the signal wasn't as clean across the other objects, the same underlying patterns emerged. The comets were no longer solid, uniform rocks. They had internal structuring, the kind that doesn't form from ice crystallization or millennia of cosmic dust accumulation, the kind that's made. At the University of Tokyo, researchers ran a surface composition model using spectrographic returns from each object's outer layer. The results came back with a mix of nickel, magnesium, trace titanium, and carbon-based polymeric material. One composite was completely unfamiliar. It displayed the reflectivity of synthetic graphite, but without the absorption profile of natural carbon chains. It was as if the material had been engineered to balance heat rejection with signal reflection. If these findings were accurate, it meant one thing: the surfaces of these once dormant comets were being altered, not by nature, not by time, but by process. 3i Atlas had passed near them less than 48 hours before their awakening, and in its wake it left behind bodies with modular surface panels, optical grids, reflective metals, and measurable cavities. These were no longer ancient frozen rocks drifting through the solar system. They were now nodes, and each one bore the same signature: structured geometry, in the exact region 3i Atlas had touched. The question was no longer if they had changed. It was who or what had changed them. By the time 6 comets had activated and begun exhibiting signs of structure, coordination, and containment, astronomers believed they had identified a pattern. But patterns, by nature, imply rhythm, and rhythm implies a source. That source would be uncovered not through telescopes or optical scans, but through radio silence, or rather, something that briefly broke it. At 0444 UTC on the morning of December 13th, the Australian Square Kilometre Array Pathfinder, ASCAP, one of the most sensitive low-frequency radio telescopes on Earth, picked up a signal burst. It lasted just under 1.2 seconds. Narrowband, low amplitude, ultra-clean, and precisely aligned with the location of the sixth reactivated comet, which had flared to life just moments earlier. The timing wasn't close, it was exact. The pulse occurred 11 seconds before the thermal flare. To anyone unfamiliar with signal propagation, this might seem inconsequential, but in astrophysics, milliseconds matter. And this wasn't a natural emission. It didn't match background cosmic radiation, it wasn't solar static, and it definitely wasn't noise. ASCAP's raw data was immediately cross-checked with South Africa's Meerkat array and Japan's Vera system. Both recorded the same spike, same timestamp, same narrowband profile. The signal was real. When the pulse was extracted and converted into a spectrogram, it showed an unnerving signature, a tightly compressed carrier tone bracketed by symmetrical harmonic peaks. That alone was highly unusual, suggesting modulation. But it was the spacing between the harmonics that made researchers pause. Each gap was identical, precise down to the thousandth of a second. What they were looking at wasn't a flare, it was a command. The term control pulse was coined informally on a private research Slack channel that same day. Scientists from multiple agencies began referring to the signal not as a broadcast or a transmission, but as a trigger, an initiator. Because every one of the prior activations had exhibited a similar, albeit fainter, precursor in the radio spectrum. This sixth one was just the clearest. More analysis followed. Time domain transforms revealed that the control pulse had not originated from the comet itself, but from somewhere farther out. When triangulated, the vector pointed directly along the outbound path of 3I Atlas. In other words, the comet hadn't just passed by the dormant objects, it had likely seeded them, and now it was instructing them to wake up, on command. To test this theory, analysts retroactively examined low-frequency radio recordings from the days leading up to each activation. Sure enough, faint control pulses had preceded all of them, each one spaced exactly 44 minutes apart, each one travelling from 3I Atlas's position to the next comet in sequence. It was as if the object had dropped markers and was now lighting them up one at a time. But even more chilling was what came next. Our seventh pulse was detected at a 5:28 UTC. No visual activation followed. No comet lit up, nothing flared. The signal simply vanished into space. That's when teams at the European Space Agency pulled up deep sky radar scans. In the path of the seventh pulse, just beyond the known cluster, was an unregistered object. No known comet, no previously catalogued asteroid. Just a cold, dark rock drifting in silence. Until now. Roughly 90 minutes later, that object began to glow. No tail, no sudden outgassing. Just a steady growing signal in the infrared range. It was heating up from the inside. No one had seen it activate. Only the pulse had gone there first. The implication was staggering. This was not reactive behaviour. It was deliberate, targeted, and time-locked. 3I Atlas was not simply awakening random bodies. It was initiating them with precision, broadcasting silent commands into the dark, then waiting. And the comets. They were listening. Whatever this network was, it wasn't passive anymore. It was responding. After the detection of the control pulse and the activation of the mysterious seventh object, scientists began to focus on a quieter, but perhaps even more revealing set of measurements. Temperature. Comets are expected to behave erratically when it comes to thermal profiles. Their surfaces are chaotic patchworks of volatile ices, porous rock, and dust layers. As sunlight strikes, heat spreads unevenly, causing unpredictable sublimation events, shifting surface temperatures, and chaotic jet formation. Some regions flare, others remain dormant. This thermal irregularity is not a flaw, it's a defining trait of natural comets. But that was not what these activated objects were doing. Instead, thermal readings gathered by the James Webb Space Telescope and supported by ESA's Infrared Space Observatory revealed something almost too clean. Every single one of the 7 activated comets shared the same surface temperature range. Not similar, identical. Within error margins so narrow, they bordered on engineered tolerance. The outer layers of each body maintained a steady state temperature of approximately 147 Kelvin, give or take less than 2, and once that level was reached, the temperature flatlined. Even more strangely, this temperature was held constant regardless of each object's distance from the Sun. Whether one was closer to the inner asteroid belt or another further out, whether their angle of incidence was sharp or shallow, none of it mattered. The temperatures remained fixed. In a natural object, this would be impossible. The only way to maintain thermal consistency across such different solar exposures is through regulation. That word, regulation, immediately raised eyebrows across astrophysical research forums. Thermal regulation requires 3 things: insulation, heat storage, and heat rejection. Earth satellites use layered insulation to protect internal systems, radiators to expel waste heat, and coatings to control energy absorption. But these are artificial systems, designed, tested, and built with intent. Nature, by contrast, is messy. Yet here were 7 activated comets maintaining thermal plateaus like engineered probes. To understand why this mattered, researchers turned to rotational data. Natural comets spin, and that spin changes how heat is distributed across their surface. Typically, one hemisphere heats first, triggering jetting that slows or speeds rotation, which then shifts the thermal balance again. It's unstable, but these objects, they weren't just spinning evenly, they were heating evenly. No nightside temperature dips, no hotspot rotation. Just smooth, global warming until a precise threshold was reached. Then stasis. This observation was confirmed using long-wave thermal imaging from ground-based instruments in Chile and South Africa. The comets displayed no localized hot zones. Instead, the entire surface of each object emitted thermal radiation in a uniform isotropic fashion, like a shell maintaining equal pressure on all sides. More than one scientist noted the eerie similarity to how spacecraft regulate onboard systems: uniform heat sinks, surface coatings, and, most importantly, feedback loops. If there were feedback systems operating beneath these cometary surfaces, they were working well. Because even as internal activity increased, jets pulsing, halos forming, dust layers shifting, the exterior temperature never spiked. The objects absorbed heat, activated, and maintained a perfect plateau. It was as if their systems were not only aware of solar input but designed to convert and hold it without breaking balance. Some argued this could still be explained through exotic chemistry, perhaps a volatile with a narrow sublimation window, or a unique crystalline structure forged in a distant star system. But that explanation failed to account for the timing. All 7 objects reached thermal equilibrium within minutes of their respective activation pulses. The temperature didn't build gradually, it snapped into place, like a system turning on. That led to a chilling realization. The energy was not just being absorbed, it was being managed, stored, even possibly redirected. These comets were no longer acting like chaotic chunks of frozen debris. They were operating like devices, and whatever internal mechanism was keeping them thermally stable, it wasn't built by accident. As astronomers tracked the newly activated objects beyond their thermal signatures, something far stranger began to emerge. Something that couldn't be explained by surface activity, internal heat, or dust halos. It was movement. Or rather, the subtle change in how these comets were moving in space. Known as non-gravitational drift, this is a normal feature of cometary behavior. As a comet approaches the Sun and begins to outgaze, it can create minor jets of vapor that nudge the object slightly off its original course. These deviations are usually small, chaotic, and unpredictable, often tied to asymmetric heating or surface irregularities, but the comets activated by 3I Atlas weren't behaving this way. Instead, their paths began to show coordinated adjustments, not random jets, not chaotic wobbles, but slow, directional drift, aligned toward a central point. Over the span of several hours after activation, each object subtly altered its trajectory. Their courses, once divergent and unlinked, began to tilt ever so slightly toward each other. Initial orbital projections, calculated prior to their ignition, showed no reason for such changes. The comets had been drifting independently for hundreds of thousands of years. Each followed its own path through the void, influenced by little more than gravity, solar radiation, and the occasional microcollision. But now they were acting like magnets responding to a common field. Their relative positions weren't just shifting, They were converging. ESA's Planetary Motion Lab ran a full simulation, integrating gravitational pulls, solar wind pressure, and known jetting data. None of it accounted for the behaviour. Then, when the seventh object, previously undetected, came online, the pattern snapped into place. The drift wasn't arbitrary, it was forming a shape, specifically a three-dimensional arc. 7 points, moving in synchronized arcs, began to coalesce into a loose curvature, akin to a partial ring or a shallow spiral. It was incomplete, but growing more coherent with every passing hour. By the time this structure was noticed, the probability that it had formed by chance had dropped to less than 1 in a billion. If this were a natural process, it would require all objects to possess the same mass, the same internal energy output, and identical exposure angles to the Sun, all at once. That's not how space works, but that's exactly what was happening. What's more, the directional drift didn't match traditional outgassing vectors. On natural comets, venting causes spin, which then influences trajectory in unpredictable bursts. But these comets weren't tumbling. Their spins remained slow, stable, and aligned, almost deliberately controlled. That meant whatever was pushing them wasn't coming from surface jets alone. It was coming from deep inside. One hypothesis, raised by a propulsion researcher at NASA's JPL, suggested internal mass redistribution. If the activated comets contained denser cores or embedded mechanisms, it was theoretically possible to shift internal mass and generate microthrust through conservation of momentum, like a satellite using internal wheels to rotate without external forces. It was a theory once considered absurd for natural objects. But now, with 7 activated comets reorienting themselves in unison, the absurdity no longer seemed so far-fetched. Even more perplexing was the rate of change. These adjustments weren't explosive or rapid. They were gentle, smooth, almost like station keeping. And with each recalculation of their projected paths, the same outcome emerged: convergence. The ring was forming faster than predicted. Astronomers weren't just watching comets drift through space anymore. They were watching them organize. And if they were organizing, then it wasn't drift at all. It was navigation. As the activated comets began to shift their trajectories into an unmistakable arc, the world's attention turned inward, literally. Beneath the dust shells and smooth, thermally consistent surfaces, a new signal was quietly emerging. One that pulsed with unnatural rhythm. One that didn't belong in any known catalogue of natural behaviour. It began with a single anomaly, an intermittent flicker deep within the core of Comet 3CL4, first detected by the James Webb Space Telescope's mid-infrared imaging sensors. At first, the reading was dismissed. A calibration error perhaps. But when the flicker returned precisely 44 minutes later, at the same exact frequency as the earlier control pulses, alarm bells went off. The flicker wasn't random, it had rhythm, and it was internal. The data showed that this wasn't just a momentary spike in temperature or reflectivity. It was a deep, pulsing emission from the centre of the object. Faint, but persistent. Not thermal, not chemical, and not gravitational. It was a unique kind of energy echo, a silent, repeating pulse of brightness from the core, showing up only in the near-infrared spectrum. Within hours, teams at the Atacama Large Millimeter Array, ALMA, and ESA's Herschel Space Observatory began scanning the remaining activated comets. The results were near identical. Every object exhibited the same internal pulsing signature, same rhythm, same timing, and in each case the pulse was delayed by a fixed interval relative to its activation. It was as if something had been inserted or activated inside the nucleus of each comet, and now it was communicating. But it wasn't broadcasting. The pulses weren't radiating outward like signals. They were bouncing inward, contained, trapped inside the object's own body like sonar echoes being played in a sealed chamber. To detect the signal at all required extreme precision and sensitivity. But once seen, the pattern was undeniable. The cores were glowing, ever so slightly, with internal pulses of energy. No known natural process could account for it. The pulses were too regular, too perfectly spaced, and too synchronized across vastly different objects. This led to a bold but increasingly accepted hypothesis. The cores were not solid anymore. They had become hollowed, or had always been hollow, containing some kind of embedded mechanism, sensor array, or possibly even reactor. Some researchers proposed that the pulses were part of a self-check system, a heartbeat. That idea quickly gained traction because, much like a biological system, the pulses seemed to respond to external inputs. After each solar flare, the pulse rhythm shifted slightly. After each jet emission, the core glow dimmed briefly before returning to baseline. The comets were, in effect, adapting. NASA's thermal imaging reconstructions showed something even more unsettling. The brightest part of each comet was no longer its surface or its outgassing regions. It was the core itself, flickering like an eye beneath layers of dust. Attempts were made to decode the flicker. Spectral analysis revealed modulation, not unlike the harmonics seen in the control pulse. There were faint sub-signals embedded within the primary glow, too weak to resolve clearly. But one thing was certain. They were not uniform. Each core had its own fingerprint of flickering intensity and duration, as if each one was broadcasting something specific to itself. No language, no binary code, just an internal ecosystem, repeating again and again. Then came the most disturbing observation yet. One of the cores, specifically the second object to activate, began to flicker faster. Not a small change, but a doubling of frequency. 12 hours later, the fifth object matched that rhythm. The rest followed suit. By midnight, all 7 were pulsing together. Faster, sharper, more intense. They weren't just alive, they were syncing. As the core flickers accelerated and synchronized across all 7 activated objects, observatories around the world shifted their focus from visible motion to something much more subtle, the spectrum. For decades, scientists have relied on spectral analysis to decode the chemical makeup, temperature, and behavior of celestial bodies. Every atom leaves a fingerprint, and comets, being primordial remnants, usually produce wide, chaotic spectral signatures. Their tails scatter light across a vast range of wavelengths, messy but rich in information. But now that chaos was vanishing. On December 12th, just hours after the last core joined the synchronized flickering pattern, astronomers at the Keck Observatory in Hawaii reported something that seemed impossible. The comet's spectra were collapsing. Not in brightness, not in scale, but in range. Their emissions were tightening into narrow, discrete bands, shedding the typical cloud of noise seen in natural outgassing. Instead of broad-spectrum emissions, each object began radiating light in only a few tightly defined wavelengths. The usual blend of ionized water, carbon dioxide, and silicate dust signals had all but disappeared. What remained was a stripped-down, surgical profile, laser-like in its precision. This phenomenon became known within scientific circles as spectrum narrowing. And while it initially triggered skepticism, suspected equipment error, local interference, or data miscalibration, multiple independent observatories confirmed the same outcome. Lick, Alma, Subaru, and even amateur radio astronomers across the globe reported identical readings. The objects had stopped behaving like dirty snowballs and started emitting like tuned instruments. The narrowing wasn't random. It followed a strict logic. Each object, though separated by millions of kilometers, began broadcasting within a similar band range, centered near the infrared, with secondary harmonics in the low microwave spectrum. The signals weren't loud, but they were deliberate. And more importantly, they were clean. No background noise, no variance, as if each comet had been fitted with an internal filter, only allowing a specific engineered frequency to escape. This shift posed a critical question. What could cause a natural object to discard its full chemical fingerprint? The answer, scientists feared, was that it wasn't natural. Spectrum narrowing is a feature of controlled systems. In telecommunications, lasers, and optical sensors, it's used to reduce noise, increase clarity, and limit detection range. If the comets were narrowing their spectral emissions, they weren't just cleaning their signal, they were hiding the rest. And the implications were immediate. With broader emissions gone, most of the internal composition of the comets became invisible to traditional sensors. Telescopes that once saw layers of dust, volatile plumes, and chaotic energy now only saw a single, silent line, a thin, crisp trace where an entire world of data used to be. In other words, the comets had cloaked themselves. One astrophysicist from MIT described it like this. It's as if someone turned off the noise, closed the windows, and left just a whisper coming through the keyhole. The comets weren't dimming, they were muting, hiding behind their own frequencies, letting only specific lines escape into the observable universe. Then came the twist. Each of the 7 activated objects, once locked to the same emission band, began to shift. Not wildly, not randomly, but methodically. One by one, they stepped their signal sideways by microwave lengths, as if taking positions on a dial. What had once been spectral harmony became spectral choreography. These shifts were still happening within the narrow band, but now each object occupied a slightly different slice of the spectrum. When plotted together, the lines looked like the rungs of a ladder, or the segments of a code. NASA's deep spectrum analyzers could no longer detect full object behavior. The narrowing had become too intense, too precise, like encryption, and for the first time, one question cut deeper than the rest. Were the comets communicating through light, or were they calibrating to receive something much bigger? With the spectral narrowing now in full effect and the synchronized flickers locked into a rhythm that seemed anything but natural, attention returned to one of the earliest anomalies, one that had started it all but was now evolving into something more sinister. It was temperature. Not just how hot or cold the comets were, but how stable they remained, despite everything happening around them. This wasn't the first time scientists had seen odd thermal behavior from these objects. Back in the early activation stages, the surfaces of the comets had demonstrated uncanny thermal consistency, regardless of their distance from the Sun or how active their jets became. But now, after the core pulses and spectrum shifts, the comets were entering a new phase entirely. They had stopped changing temperature. Every known comet undergoes thermal flux. As it rotates, one side heats, the other cools. As solar radiation increases, surface volatiles sublimate, releasing heat and causing further fluctuations. But the 7 objects now locked in the 3I Atlas arc were doing none of that. They had each reached a perfect thermal plateau, and stayed there. Each comet held steady at its own specific temperature, unchanging over the course of an entire solar day. No diurnal variation, no heat spikes from jetting, no thermal wake as they cut through solar wind. Nothing, just a flat, undisturbed signature across every observing instrument. To the human eye, this wouldn't mean much, but to astronomers, and especially thermal physicists, it was a glaring red flag. Because it violated everything we know about energy exchange. In a natural system, energy is always in motion. Even frozen comets absorb and re-radiate solar energy in a never-ending dance. But these objects appeared to have reached thermal equilibrium and locked it into place, each one with its own precise temperature, maintained across every axis and at every depth that could be measured. Infrared imaging confirmed that even deep surface layers showed no change. Subsurface scans that should have revealed heat differentials showed nothing but monotone returns. It was as if each comet had installed its own internal thermostat and refused to budge even a fraction of a degree. This behavior sparked another wave of theories, none of which were comforting. Some scientists suggested the presence of phase change materials, exotic compounds capable of holding large amounts of heat without altering temperature, much like salt hydrates or paraffin in Earth-based thermal regulation systems. But for 7 independent objects, scattered across millions of kilometers, to be using such materials identically, that stretched the limits of coincidence. Others proposed something more deliberate: active thermal regulation. This would imply that the comets weren't just passively maintaining temperature, but actively controlling it, like a spacecraft using heat pipes and radiators, or worse, like an intelligent system adjusting internal operations to match external conditions. It became even harder to dismiss when ESA's thermal reconstructions showed small fluctuations in solar intensity, such as minor solar flares or changes in heliocentric position that should have altered surface temperatures by measurable degrees. But the comets ignored all of it. No response, no change. The plateau held steady. It was as if the objects were insulated from the sun entirely. And then came the chilling part. When compared side by side, each of the 7 comets had reached its thermal plateau at exactly the same time, down to the hour. Independent of location, independent of surface composition, all 7 locked their temperatures at once, as if a switch had been thrown, as if the environment no longer mattered. The term adaptive thermoregulation began circulating in private Slack channels and late-night Zoom calls between observatories, a term that doesn't apply to frozen rocks, but does apply to systems with internal feedback loops. These comets weren't surviving the solar environment, they were ignoring it. As the temperature plateau locked itself in place across all 7 activated comets, thermal irregularities began to vanish entirely. But just when it seemed the objects had settled into a stable, almost lifeless state, new activity erupted, only this time it defied the most basic laws of cometary physics. Jets, but not the kind directed away from a sunlit surface as expected. These were doing the exact opposite. They were firing directly toward the sun, anti-solar jets. The first instance was recorded by Japan's Hinode Solar Observatory during a routine coronal mass ejection scan. A jet of particulate matter was seen firing from one of the Atlas-aligned comets, not away from the solar heat but directly back into it. For a moment, Mission Control thought it was a flare artifact, a lens ghost. But the motion was consistent across frames. The material wasn't drifting, it was accelerating, pushed out forcefully from the shadowed side of the comet and into the direction of the sun. When news of this broke, it sent shockwaves through the astrophysics community. Every natural comet, regardless of size, mass, or chemical makeup, vents material in one predictable direction, away from the sun. This is because solar heat causes volatiles within the comet to sublimate. That process generates pressure, which pushes gas and dust outward. The result is a jet, sometimes chaotic, sometimes controlled, but always solar opposing. But the jets being observed now were moving directly against that pattern. More strange still, they weren't chaotic. They were precise. Data from SOHO's LASCO C3 instrument showed that each jet originated from an exact point on the comet's surface, opposite the sun. The jets didn't drift, spiral, or fragment like natural vents. They emerged in tight columns, narrow, sustained, and constant in pressure. It was propulsion, not outgassing. These weren't escape events, they were maneuvers. Within a 12-hour span, 5 more comets followed the same pattern, each releasing a fine, directed plume toward the sun. Not simultaneously, but in perfect sequence, spaced apart by near equal intervals. The material wasn't volatile gas or ice either. Spectral analysis showed traces of silicate dust and heavy carbon, chains, not the typical signatures of surface melting, but something more refined. This suggested that the jets weren't thermal reactions at all. They were structural discharges, like ballast being ejected or energy being redirected. Some researchers proposed a terrifying theory, that the jets weren't just propulsion, but part of an internal balancing system. If the objects had reached a perfect thermal plateau and were absorbing solar energy without changing temperature, then what were they doing with the excess energy? The answer might be, they were expelling it. Not through radiation, not through infrared emission, but through kinetic redirection, using material jets to burn off force, like a flywheel dumping mass to maintain speed. Or worse, like a stabilizer keeping its host pointed exactly where it wanted to be. NASA's JPL ran comparative models between these jets and known examples of chemical and ion propulsion. The pattern wasn't identical, but the ratio of mass to thrust was disturbingly close. And when this was entered into the drift models for each object's trajectory, something unexpected happened. The jets corrected for solar gravity. Each one was timed to counteract the smallest tug from the sun, precisely balancing the inward curve of the object's motion, keeping it from drifting closer. Not escaping, but holding position. It was station-keeping. The term wasn't used lightly. It's the language of satellites, not comets, but it was the only term that fit. 7 objects, aligned in an arc, flickering from within, spectrally narrowed, thermally sealed, and now, jetting toward the sun, just enough to stay locked in perfect place. Natural behavior ends somewhere. This had crossed that line. As the anti-solar jets maintained perfect station-keeping, researchers expected a degradation in optical clarity, typical for any object venting material into space. Dust clouds should have formed, surfaces should have become uneven. Instead, what happened next broke every visual modelling rule in astrophysics. The objects became clearer. On the evening of December 12th, the Hubble Space Telescope completed a targeted imaging sweep of 4 of the activated comets. The goal was to observe surface texture changes caused by jetting and internal heat pressure. But what the team saw was the exact opposite. The surfaces weren't rough, they were refining, becoming smooth, angular, and alarmingly uniform, not randomly and not symmetrically in the way natural erosion might occur, but with intentionality. Refined geometry began to emerge, flat planes, angled reflections, segmentations that mirrored polygonal patterns, as if the outer shell of each comet had been gradually restructured, not by impact or decay, but by design. The term used in the report was reflective geometry. Under specific lighting conditions, particularly when illuminated by forward-scattered solar light, the comets revealed specular reflections, the kind you'd only expect from polished surfaces. This wasn't the dull glow of dust-covered ice. These were clean, mirror-like surfaces appearing in distinct patches across the objects' bodies. The first assumption was crystalline surface development, something that can happen under extreme thermal cycling. But spectroscopy ruled that out. There were no known crystalline compounds forming on the surface. In fact, reflectivity was increasing while traditional outgassing elements were decreasing. The comets were not crystallizing. They were evolving into reflectors. Why that matters is because of what it implies: internal orientation. To reflect light in controlled angles across a rotating body requires exact alignment, not just of surface panels but of motion itself, and the comets were doing just that. Observations from Earth-based optical arrays, including those in the Canary Islands and Chile, confirmed that the reflectivity from each object was not just rising, it was rotating in predictable patterns. The implications were staggering. Each object now had a signature face, a side that periodically reflected light with greater intensity than any other. These weren't random flares. They were phase-locked pulses of light that aligned with the same internal timing as the core flickers and spectral shifts. When plotted across time, the reflection events matched the pulse windows exactly. In simpler terms, the comets weren't just reflecting light, they were sending it. Even more disturbing was the angular precision. Using the Keck adaptive optics system, astronomers measured the exact degrees of reflection deviation. They found that each object's most reflective side was positioned along a calculated trajectory, directed not away from the Sun, but toward Earth's orbital corridor. The angles weren't aligned to Earth itself, but to the vector path our planet would follow across the next 6 days. The reflection wasn't passive, it was predictive. This opened the door to one conclusion that had been quietly building in the background. The comets were acting as directional reflectors, potentially communication devices, or worse, components of a larger optical array. Whether these were mirrors, signal routers, or passive receivers remains unknown. But when 7 separate objects begin aligning mirror-like planes toward a specific orbital vector, while simultaneously emitting synchronized pulses from within, it becomes impossible to maintain a purely natural framework. Reflective geometry in this context wasn't a visual artifact. It was a message, encoded not in language but in alignment, a geometry that watches, a geometry that waits, and in the silence of deep space, it had turned its reflective face toward us, just ahead of schedule. As the object's surfaces transitioned into mirror-like planes and their reflective pulses locked into Earth's future orbital path, one final expectation still lingered in the minds of even the most skeptical scientists, an expectation rooted in centuries of celestial observation: fragmentation. For any comet behaving this erratically, experiencing synchronized core pulses, anti-solar jets, thermal plateaus, and now reflective geometry, fragmentation is inevitable. It's not a matter of if, but when. The pressures alone should have torn them apart. Under normal conditions, comets are fragile structures, a mix of porous rock, volatile ice, and organic dust loosely held together by low gravity. When exposed to solar radiation, the outer layers crack, vents rupture, and internal stresses build. Most comets break apart long before their return orbits are complete, especially if they venture anywhere near the Sun's influence. But these didn't. Despite their complexity, despite their synchronized emissions and propulsion-like jets, not a single one of the 7 activated comets showed any sign of splitting, shedding mass, or even flaking. In fact, the opposite was occurring. They were becoming more cohesive. High-resolution scans from both Earth-based arrays and the Parker Solar Probe confirmed that the object's silhouettes had not only remained intact but had grown smoother. Micro-variations in contour, expected from standard erosion, were disappearing. The surfaces weren't degrading, they were consolidating, hardening. And this caught the attention of planetary defense teams worldwide. In every known case where a comet begins to exhibit high internal activity, flickers, temperature shifts, or gas jets, fragmentation follows. Outgassing fractures build over time, and the internal pressure eventually overcomes the weak gravitational cohesion. But these 7 objects had survived solar proximity, remained synchronized, and even performed directional jetting without losing a single shard. There were no debris trails, no tail fractures, no thermal hotspots indicating crust rupture, not even small companion objects drifting nearby, a common feature among unstable or pre-fragmentation comets. This absence wasn't just odd, it was alarming, because it suggested a kind of internal integrity that natural objects do not possess. To hold shape under multiple stress events, thermal, magnetic, directional, and structural, requires reinforcement, something binding the core, something keeping the geometry not only intact, but stable enough to support reflective surfaces and synchronize behavior. It was as if each comet had been rebuilt from the inside out. Some scientists floated the possibility of ultra-dense core material, but core density typically reveals itself in gravitational effects, such as small perturbations in nearby satellite motion or gravitational lensing at the outer edges. None of that was observed. Instead, what was observed was uniformity. Mass distribution across each object was startlingly consistent, something only possible through design or active self-regulation. And so, a new word entered the quiet. Corners of internal briefings, containment. The idea that the objects weren't held together by mass alone, but by an internal containment structure, mechanical, magnetic, or something more advanced. A force or field keeping the internal systems from tearing the outer shell apart. A structure that responds not with cracks but with silence. No stress fractures, no faults, no visible strain. This was not the behavior of snowballs drifting through solar fire. It was the behavior of constructs. The implications shook the foundation of planetary modelling. Because a natural comet, no matter how exotic, is supposed to fall apart when it behaves this strangely. But these didn't, and every hour they remained whole, every kilometre they covered in perfect formation, and every mirrored pulse they fired toward Earth's orbital path. They became less like anomalies, and more like occupants. They weren't disintegrating, they were holding, advancing, waiting. Not a single fracture, not a single failure, only silence, and 7 intact objects moving with the calm precision of something built for exactly this journey. Even as fragmentation failed to appear, scientists clung to one final thread of cometary predictability, the tail. If everything else defied classification, no outgassing, no heat variation, no dust shedding, surely the tail would still behave as expected. It had to. But then the delay happened. It was first noticed by the Arecibo Replacement Radar Array in Argentina, now repurposed to monitor long-duration reflectivity trails in the upper atmosphere. The team had begun comparing past data on conventional comets, tracking the delay between solar particle interaction and tail echo signatures, especially when Earth-facing telescopes lost direct sight. Normally, a comet's ion tail lags behind by a predictable margin, bending gently from the sun as solar wind pushes charged particles away. The timing between jet activity and corresponding tail formation is almost instantaneous on astronomical scales. Hours, maybe minutes, never days. But on the morning of December the 12th, something broke that pattern. The forward object in the 3i Atlas array, one of the 7 aligned bodies, produced a visible directional jet at 0211 UTC. This was confirmed by 5 independent solar observatories including India's Astrosat. The jet was clean, narrow, and unmistakably artificial in its stability. And then, nothing. No tail. No ion dispersion. No reflective trail. In fact, Earth-based telescopes scanning the object's wake in infrared and ultraviolet bands found a total absence of residual material. It was as if the jet had left nothing behind. 26 hours later, everything changed. A pulse returned. A soft, narrow echo, like a whisper coming back from a canyon too deep to see. It wasn't visual, but radio. A high-frequency backscatter signal, bouncing from the exact angle where the jet had once fired. The echo pulse had the same amplitude, envelope as the jet signature, just slower, much slower, delayed. This was not how tails behave. They don't wait. They don't pause. They don't appear long after the originating event. But now the same pattern began repeating. Each of the other 6 comets followed with identical behaviour. Jet activity would occur in precise intervals, and each time a backscatter pulse would arrive from deep space more than a day later. Always delayed, always directionally consistent, but never visible to the naked eye. Scientists had no choice but to abandon the idea that they were observing traditional ion tails, because what was coming back wasn't matter, it was signal. The phrase tail echo delay was coined not to describe a comet's wake, but to explain the arrival of unknown radio signatures that mimicked jet behaviour long after the visual event. Some called it artifact noise, others believed it to be scattering from undetected companion bodies. But none of those explanations held, because the echoes weren't fading, they were strengthening. With each successive pulse, the returning signal grew cleaner, tighter, more structured. Some patterns even began repeating in frequency clusters, forming short sequences that hinted at modulation. If true, this was no longer about comet tails, it was about information. Were the comets bouncing signals off deep space structures? Were they receiving delayed responses? Or worse, were they transmitting out and receiving back echoes of something they had already spoken to? The possibilities were deeply unsettling. Because delay, when deliberate, means distance. And if each pulse was indeed a sense signal bouncing from an external target and returning late, then something out there was responding. Not from within the array, not from between the comets, but from farther out, beyond them. And it wasn't just one delayed echo, it was a cycle, a rhythm, a delayed call and response. The tails hadn't vanished, they had evolved, from gas and dust into language. While the echo delays were still being analysed by deep space signal labs across Europe and Asia, another layer of behaviour emerged, one that couldn't be seen with the naked eye, or even in traditional optical imaging. It revealed itself only through polarisation. At first, the readings were dismissed. Polarisation changes happen often in deep space. Light scatters off dust, ice, or magnetic fields, and the orientation of that light rotates as it travels. But polarisation patterns are usually random or steadily decaying. They don't repeat, they don't lock into cycles. But that's exactly what these objects were doing. On the morning of December 12th, Japan's Subaru telescope captured a brief, rhythmic oscillation in the polarized light coming from one of the lead objects in the Atlas array. At first, the signal seemed like a glitch, just a flutter in the atmospheric correction filters. But when the same wave pattern appeared 4 hours later from a second comet, and again from a third one 6 hours after that, a pattern began to form. The polarization wasn't random, it was repeating. Across all 7 objects, the light being reflected, especially off their geometric mirror-like surfaces, began showing synchronized changes in polarization angle. Not chaotic, not drifting, but phase-locked. Each shift followed a structured rhythm, rotation, hold, reversal, then again and again. This wasn't just strange, it was mechanical. Because natural bodies don't produce repeating polarization signals unless some rotating structure, filter, or field is causing it. For this to happen across 7 separate objects simultaneously meant either they shared the same internal orientation system, or were all responding to a single external field. Neither possibility was comforting. Polarimetric mapping from Chile's VLT, Very Large Telescope, began layering the shifts into a 3D model. The result was alarming. The angles of polarization weren't random scatter, they traced arcs, concentric intersecting arcs that, when projected outward, converged on one fixed point in space, a location just ahead of Earth's current orbit. It was like the objects were sweeping light in a spiral pattern, rotating their internal filters or reflective plates in exact intervals, projecting something not for us to see, but for something else to detect. That's when radio observatories stepped back in. When the polarization rhythms were overlaid with the tail echo delays from Chapter 18, the intervals matched. Not the exact frequencies, but the timing. Every polarization reversal occurred just before the delayed radio echoes returned. This wasn't coincidence, it was coordination. The comets weren't just sending light, they were timing it. The orientation of polarized reflection was being used as a metronome, a heartbeat. It marked when to expect a return signal, when to change facing, and perhaps when to move. In short, the objects were in sync with something. Whether it was internal communication between them or synchronization with a distant receiver, no one could say. But there was one more disturbing realization that came out of the data. Polarization like this isn't just directional, it's encoded. And in this case, the rotation pattern carried data density far too structured to be random. Some began to speculate that the 7 comets weren't simply navigating. They were communicating in an entirely different format, using light not just as a signal, but as a channel. A narrow band of high frequency, repeating polarized light aimed across interplanetary space. Some began calling it vector whisper, a language of light rotation that existed beneath ordinary detection levels. But language implies intent, and intent means these comets weren't alone. They weren't just orbiting or holding formation or waiting. They were talking to each other, or worse, to someone else. And Earth was now caught in the path of that conversation. As polarized light continued its silent rotation across deep space, and tail echoes returned in eerie, time-delayed pulses, attention briefly turned to something unexpected, something overlooked amid the synchronized ballet of the 7 primary comets, the 6th object. It wasn't forgotten because it was unremarkable, quite the opposite. The 6th object in the 3i Atlas array had remained conspicuously quiet. For days it emitted no core flickers, no antisolar jets, no sudden realignments. It had drifted along the shared orbital corridor with precise pacing, shadowing the others without deviation. And for most observers, it was considered the control group, the anomaly that didn't behave like the rest. But then it stopped. Not slowed. Not veered. It stopped. On the night of December the 12th, shortly past midnight UTC, tracking logs from the Deep Space Network in Canberra registered an abnormality. While all other comets maintained their expected velocities and trajectories, the 6th object's forward motion reduced to near zero over a 90-minute window. This wasn't a gradual deceleration caused by solar drag or gravitational interference. It was an abrupt halt, with no physical explanation. Nothing around it had changed. No jet activity. No rotational instability. The object simply froze. At first, analysts suspected a measurement error, perhaps a radar blackout or transient solar interference, but confirmation soon came from multiple observatories, including low-frequency radar from India and thermal drift tracking from the European Southern Observatory. All agreed, the 6th object had stopped, precisely, silently, and deliberately. And then came the real shock. Within 3 hours of halting, the 6th object began emitting backward pulses, not toward the sun, as most natural outgassing would behave, but directly opposite the direction of travel, targeting the exact route it had come from. These pulses were low in energy, but narrow and focused, like a kind of scanning beam, and each one was followed by silence. No reflection, no tail, just dark space, until the 7th pulse. A faint glimmer returned. Not light, but motion. From the far end of the scanning path, deep in the object's wake, a shadow began to move. Slow, faint, deliberate. Another body. Small at first, barely distinguishable from background noise, but gaining contrast with each pulse. What emerged was a secondary structure, trailing the 6th object by several thousand kilometers, previously undetected due to its perfect alignment with the larger body's wake. The implications were enormous. Was this a companion probe? A detached fragment being called back? Or something far more deliberate? A shadow craft that had been waiting for a signal? One by one, analysts began feeding the imagery through shape filters, reflectivity maps, and motion tracking software. What they found was deeply unsettling. The trailing body wasn't tumbling like space debris. It wasn't exhibiting gravitational lag like a natural companion. It was matching the pulses, adjusting its trajectory to every backward burst emitted by the 6th object, as if each pulse wasn't a signal for us, but a summons, and the summoned body responded like it knew what to do. Eventually the 2 objects aligned, one ahead, one behind. Then, together, they began to rotate. Not just spin, but rotate around a shared invisible axis, syncing like a two-part key aligning itself to a larger mechanism. The rest of the comets continued forward, unaware, unchanged. Only the sixth object had broken formation, and in doing so, revealed something far stranger. It wasn't acting alone, it was equipped. And that equipment, whatever it was, had been hidden until now, shielded by wake geometry, masked by silence, and activated only when the timing was right. In every fleet there's always one with a different task, and now we knew which one it was. The sixth object wasn't a watcher, it was a controller, and it had just awakened something in its trail. The moment the sixth object revealed its silent partner, every model that had tried to chart the 3i Atlas trajectory became obsolete. Analysts across multiple space agencies scrambled to reframe the event, not as a deviation, but as an escalation. Because whatever signal had passed between the sixth object and its shadow, it had consequences. By dawn on December 12th, a subtle curvature appeared in the trajectory of all 7 primary bodies. Not chaotic, not reactive, but fluid, like marionettes tracing arcs in concert. Telescopes in Hawaii, Chile and Australia captured the drift first. Small, almost imperceptible nudges to the vector. A shift in degrees so small that most systems filtered it out as rounding error, but it wasn't. When overlaid on a full solar system simulation, the convergence became clear. The objects were not maintaining separation anymore. They were adjusting inward, pulling toward a central corridor, one that cut directly across Earth's orbital path. In previous days, each comet had held to its own radial arc, with minor harmonics suggesting awareness of one another. But now that awareness had turned into precision. Their spacing compressed, their drift dampened, and most critically, their angular alignment with Earth tightened. Within 2 hours, every observatory running simulation protocols updated their hazard scores. Not because of imminent impact, but because of trajectory convergence with Earth's gravitational window. This is the corridor through which any fast-moving object, even without direct collision, can pass close enough to interact with Earth's magnetosphere, atmosphere, or orbiting infrastructure. Passing through it at the wrong time means electromagnetic interference, atmospheric disturbance, or worse, redirection via gravitational slingshot. And now all 7 comets, plus the shadow object from Chapter 20 were threading the same needle. By mid-morning, the data reached the inner circles of planetary defense teams. What concerned them wasn't speed, it was coordination. Each comet adjusted its position not in isolation, but in reference to the others. A long-range laser array in South Africa confirmed that reflective pulses, first seen in previous polarization studies, were now moving laterally between the bodies. It was like watching satellites adjust into a launch corridor, each maintaining both distance and direction. And here's what made it undeniable. Every adjustment moved the objects closer to Earth. Not a single one curved away, none decelerated, none expanded their drift to reduce risk. They were tightening the group, flowing inward with a grace that no natural formation could replicate. This wasn't gravity. This was intention. Even the sixth object, after its dramatic standstill and the emergence of its shadow counterpart, resumed forward motion, but now from a central position, as if acting as the lead. It did not rotate randomly. It oriented toward the Earth vector and remained locked there. Some observers held out hope that this was just a flyby, that perhaps the objects had always been on a path to intersect Earth's orbital zone, but not Earth itself. But that hope faded fast. Because the latest thermal models showed minor orientation shifts, specifically among the forward-facing reflective surfaces. They were beginning to tilt, not up, not outward, toward Earth. More concerning still, narrowband tail echoes were no longer appearing behind the objects. They had reoriented ahead, forward-facing, a pulse signature directed not to their own past trajectory, but to their future intersection. And Earth sat directly in that path. This wasn't approach anymore, this was convergence. And as the geometry aligned and each body took its place in the invisible corridor, the message could no longer be ignored. They weren't drifting, they weren't lost, they were coming.